First of all, I'm going to talk about some old invariants of John Milner's for studying links, collections of knots. Let's just start with something very basic and make sure that everyone knows what I mean by the trivial knot, right? So first of all, a knot is a circle, right? A knot is an oriented circle embedded in, I can think of it as R3, but it's convenient to have compact manifolds. So we typically throw in a point in infinity and think of it as contained in S3. And it's trivial, K is trivial, if this knot, S1 and S3, bounds a disk in S3, embedded. Right? So just so make sure we understand what that means, let's just take a look. If I take S3, that's the boundary of D2 cross D2, which is D2 cross S1, union S1 cross D2. And inside here, of course, I have S1 cross 0, the origin. And that clearly bounds this disk, right? So there's a nice model for the trivial knot, right? So that's the trivial knot. Maybe I'll call that T for trivial, right? And we could talk about the exterior of a knot, in particular the trivial exterior of a knot K is just what I get by taking S3, and I remove the interior of a copy of a tubular neighborhood of K, a neighborhood of K, right? So that gives me a compact manifold whose boundary of EK is, of course, the knot cross S1, because a knot has a trivial tubular neighborhood. And so in particular, if I take the complement of the trivial knot, I remove an open neighborhood of the trivial knot. That's an S1 cross an open D2. I'm left with D2 cross S1. And so in particular, if I take pi1 of the exterior of the trivial knot, that's Z, because it has the homotopy type of a circle. Right? So that's very, very basic things. And a deep theorem of Papakyriakopoulos. I don't know if I know how to spell Papakyriakopoulos. I don't know if I spelled that right. It's close. Papakyriakopoulos, maybe that's an A, is that if pi1 of the exterior of the knot is Z, then K is the trivial knot, right? It's if and only if. A knot is trivial if and only if pi1 of the exterior is Z. That's deep. It's very hard. One has to prove what's called the loop theorem that tells you that if you have a null homotopic curve and a three-manifold that bounds, it's null homotopic, so it bounds some immersed disk, and if in a neighborhood of the boundary it's embedded, then someplace in that three-manifold there's an embedded disk with the same property. That's a very hard theorem to prove. It was proven in the 50s by Papakyriakopoulos. But it implies that, in fact, that a knot is trivial if and only if its fundamental group is Z. Now, what I'm really going to be interested in today is not knots, but links. Well, that has knots as a special case. So a link, L in S3, is an embedding. An oriented embedding is an oriented submanifold with L, say, diffeomorphic to a collection of circles. And I'll call this an M component. So this is just a collection of knots. Right? And I'm going to be particularly interested in the notion of concordance, which is a very central and old notion going back to Fox and Milner. L naught and L1 are concordant if there exists some submanifold C, some surface C in S3 cross I, such that, and we'll assume that it's smooth for this discussion, such that C intersect S3 cross I equals Li, I equals 0 and 1. So, so that just says that the picture I drew for knots the other day in the colloquium, I'll just remind you of the picture I drew in the colloquium for knots, but it works the same way for links. You have S3 cross I. You have some knot here, say K1. So this is S3 cross 0, 1. And you have some knot here, K0. And in between, you have an annulus embedded. But the annulus may be embedded in a non-trivial way. It may be all knotted up in there. It might do something like this. Right? So the annulus between K0 and K1 could be very badly embedded. But if so, we call that a concordant links, or that's concordant knots in this case. Links are collections of knots, so you'd have to have a cylinder. You'd have to have an annulus for every pair of knots, right? Little comment: these components, the components of L, these are ordered. Right? When I talk about a link, I have a first, a second, a third component. So I have to have a collection of annuli between the first component of L0 and the first component of L1, second component to second component, all disjointly embedded in there. We call that concordance. And then this surface is called C. This is C here, is called the concordance. Now, I'm going to try to make this talk as much as possible independently. It's a different topic, really, although a related topic. I'm going to try to make it as much as possible independent of the colloquium I gave the other day, because I don't know if people were there. But I will say that I gave an example of a knot which was null concordant, concordant to the trivial knot. Oh, a little comment here, by the way, just a little more. Note the following. Right? L is slice if L is concordant to the trivial link. Which just means that each of the components, the components bound disjoint embedded disks. Right? And if that's the case, well then I can take that trivial knot and I can make it bound a disk. And so the net effect is that the knot itself will bound, in fact, a disk in D4. So this is the same as L bounds disjoint disks in D4. So to be slice, to be concordant to the trivial link is the same as saying that the components bound disjoint disks in the 4-ball. So I gave an example last time. I drew an example. I never find these easy to draw. But let me just show you one example. I won't talk about it in any detail. I did it at the colloquium. But I'll at least remind you of what these things can look like. Let's see. I'm sorry, that's not what I wanted to do. Oh, just here, there it is. There's an example of a non-trivial knot. And it's not too hard to show that this is slice. I did so. I talked about why that was true at the colloquium, but it's, just to so I think I'll pass actually. Well, I can show it to you quickly, right? You choose a disk here. There's an obvious disk sitting around in here. But it intersects itself. So what you do is you cut holes in that disk. Now that all takes place in R3, right? In S3. So now you have an extra dimension to work with. So in S3 cross I, or in R3 cross I, in the extra dimension, you have a set of, for each of these circles, you have a set of points x, y, z, 0. And I just take the cylinder, which is x, y, z, t, as t goes from 0 to 1. And that comes out into a parallel copy of R3. And in that parallel copy of R, so I attach the cylinder there. And in that parallel copy of S3, that circle now bounds a disk. And I can do that with each of these circles, and I can see that that's a slice link. So that's one easy way to see that these are slice links. That this is an example of this is a slice knot. I could create a slice link by introducing similar intersections here. I could now do something like this. And then just draw another copy of the same knot, right, here. And that would be a link which is sliced for the same reason. I would cut a hole here, and I would cut a hole there, and then I would just fill in a disk with the extra dimension. So it's not hard to find sliced knots and links in that way. Now, I'm going to talk about some old work of Milner's, and to do so, I'm going to need to talk about the lower central series, so of a group, right? So G a group, right? Then the lower central series is defined by just a sequence of subgroups, of normal subgroups, defined by gamma 1 of G is just G. And gamma n of G will be what I get by taking the commutators of gamma of G and gamma n minus 1 of G. Okay. Now, if I take the extension, right, if I take G mod gamma n plus 1 of G over G mod gamma n of G, then the kernel is gamma n of G modulo gamma n plus 1 of G. And it's not hard to see that that's, in fact, if I take the commutators of G and Gn and mod out by the commutators of G and Gn plus 1, in particular, that's clearly an abelian group. And furthermore, the action of G by conjugation on that group is trivial. So that's a central extension, right? And this is the most rapidly descending central sequence of subgroups, such that the quotients, such that the associated groups you get, extensions you get this way, are central extensions. So that's a sequence of subgroups of G that decrease as rapidly as possible, guaranteeing that you have central extensions like that. And in particular, G is nilpotent, right? So G is nilpotent, remember, means you've got some descending sequence of normal subgroups whose quotients are abelian. So G is nilpotent, are central rather, whose quotients like this are central subgroups. So is nilpotent if and only if gamma k of G is 0 for some Z. I should write it this way, as the identity group for some Z, for some k rather. Okay? So that's the lower central series of a group. Now at last we can talk a little bit about Milner. Let me give you an example of that maybe first. Let me just give you I'm trying to keep the talk fairly basic here, at least initially. So there's no reason maybe people are not, it's a standard thing to see in a group theory course, but maybe it can't hurt to do a simple example. So suppose G is the group UT, where UT U inverse equals T inverse, and let's let U squared be 1. So you can write that group. That group abelianizes to Z. If I abelianize this group and I look what I get, well, let's just say if I kill T, I get the group generated by U, which has order 2. And the subgroup is the subgroup generated by T, but that's normal. And so I get this group, and that's the infinite dihedral group. So this is generated by T, and this is generated by U. Right? Now, if I take the commutators in there, well, let's see. Of course, u commutes with itself and t commutes with itself, so I just have to worry about the commutator of u and t. And if I do tu, t inverse u inverse, right, the commutator of t and u, I get t squared. And so gamma 2 of g is the subgroup of all things of the form z to the 2n. And then I can take the commutators of t squared with u to figure out the next lower central subgroup. And that's t squared u t to the negative t u inverse. And that's t to the fourth. And so gamma 3 of g equals t to the 4n, n and z, etc. Right? So in particular, if I take g mod gamma n of g, I just get z 2 to the n minus 1, I think, mod 2 to the n minus 1, semi-direct product z2. And that's the dihedral group. That's a dihedral group. So the lower central series quotients of the infinite dihedral group are dihedral groups. A simple example. Okay, so what does this have to do with links? Well, it goes back to a very old theorem of Milner's. One of the oldest theorems of Milner's. Theorem Milner. I think it was 1954 he proved this, but I'm not sure. I think it appeared in 1954. Milner was interested in taking a look at, so let L and S3 be a link. And let pi equal pi 1 of EL. Now what one can do is there's a nice collection of elements in there. If I have my link, say that's K1 and that's K2, etc., then I can take a base point. And I can, these are oriented, remember. I can take a base point and I can draw a path up. I always forget which way is which. Let's see, if I use the right-hand rule, I guess this way. Right? I can draw a path up and I can take the curve that links that knot once. Right? And let's call that x1, x2. Okay? And then I can do the following as well. I can take the curve that goes parallel to the knot. And we'll call that lambda 1. Now that's not well defined. But it turns out if you take the complement of the knot, the first homology is free abelian, or the link, the first homology is free abelian, just by Alexander duality, is free abelian given by the number of, the rank, which is the number of components. And so I can take that knot and I can compute I can take that curve and I can compute its homology class in the first homology of the complement. And that could be some multiple of the knot K1. So if that's the case, then I just unwrap it around K1 by wrapping it around a few times so that it's null homologous, right? And I get this collection of parallels, and this is called lambda 1, lambda 2, and these will be called the longitudes and the meridians. And so what Milner was interested in doing is he was interested in computing the nilpotent quotients of this group. So Milner took a look at the group pi mod gamma k of pi. Right? That is pi, the fundamental group of the knot, of the link rather, modulo the kth term of the lower central series. And he proved that this is actually generated by the meridians. Once I kill the lower central series, they're a complete generating set. Now, there are other relations which are obviously there, right? I have the generating set, and if I mod out by k-fold commutators, then I'm clearly going to get k-fold commutators in the free group on the meridians. Those are clearly there. And there's another obvious set of relations. Every time I have a knot, I have a torus, which is the boundary, a torus which is on the boundary of that three-manifold. And a torus means I have two elements that commute. The longitude and the meridian commute. So I also have these relations, x1 lambda 1, xm lambda m. And Milner's theorem is that this is, in fact, an isomorphism. Okay? Very old theorem of Milner. Now, why did he care? Well, his idea was, let's note something. This implies that pi mod gamma k of pi is isomorphic to the free group modulo gamma k of the free group on x1 through xm, if and only if the lambda 1 through lambda m lie in gamma k minus 1 of pi. Right? In that case, these become k-fold commutators, and they get absorbed into here. So I get the free nilpotent group. So the free nilpotent quotient is isomorphic to the link group quotient, right? The nilpotent link group quotient, if and only if the longitudes lie deeply in the lower central series. And so Milner's idea was, great, well, let's measure the longitudes as elements in this group and try to extract numerical invariance from that. That was his idea. Okay? And he did so using a result of Magnus. This is very old mathematics. In a minute, I'll tell you a little story about Milner. Not really about Milner, about me. But it relates to Milner. Okay? It relates to Milner's work. So now there's the result of Magnus. Magnus had shown earlier that in fact there's a homomorphism from the free group, we'll call it phi, onto the power series ring, or to the power series ring. In non-commuting variables, say T1 through Tm. So this is free on the meridians and on the xi's, and then I get something in the non-commuting variables in the ti's. This takes xi to 1 minus ti, and it takes xi inverse, well, to the obvious thing, ti plus ti squared plus dot dot dot. Now this is non-commuting. Ti, tj, and tj, ti aren't equal. And then his theorem was that a word in the free group, a word is in gamma k of the free group if and only if phi of that word equals 1 plus terms of degree greater than or equal to k. Remarkable theorem, very old classical theorem, quite a beautiful result. And so Milner said, great, I have everything I need now. See, I can take that longitude and I can write it as a word in the xi's, and then I can compute this to see whether or not it's a word lying in the kth lower central subgroup, or the k minus 1 lower central subgroup. So here's what he defined. Here's the Milner invariance. This is still an enormously active field of research. 50, what is it? Roughly 50 some years later. I don't know, I can't count. Right? This was 54, I said. He defined Milner's invariance 59 years later. 59 years later, there's a lot of activity in this area still. So, of course, there are much more different ways of thinking about them, and we'll discuss that. So Milner's invariance. I was reminded in a conversation a few minutes ago that Milner's invariance had been playing a sort of significant role in number theory recently, too. Well, in the last 10 years. That there are analogs of Milner's invariance for studying things about ideals. Very interesting work. Okay, so we have L and S3, and let's assume that the longitudes, we'll do this inductively. We'll assume the longitudes lie in gamma k minus 1 of pi, of the link group. And then let's let I1 through ik minus 1 and another j So I have k numbers here, b between 1 and m. And Milner defined, Milner defined what he called mu bar of I1 through ik minus 1j to equal the coefficient of t to the I1 through ik minus 1, that monomial, in phi of lambda j. Right? And of course, it follows from the above that f mod fk is isomorphic to pi mod pi k, or pi k plus 1, if and only if mu bar L of length, we'll call this k, we'll call the length of the mu bar invariant. And then for any such thing of length k, any such sequence of digits in length k, of length less than or equal to k are equal to 0. Okay? So that was Milner's idea. Now Milner he couldn't prove a lot about these things. He proved that they were invariants. He looked at higher order terms, and there was some indeterminacy, and he calculated a little bit about this indeterminacy and some relations. Somehow there are some relations about how the different for different strings of, sometimes for different linear combinations of these of invariants associated to strings of length k, you can get that some sum is equal to another one. There are certain relations among them. He computed things about that. He did some examples of links with whose first non-vanishing Milner invariant was very high, but very few examples. He really couldn't do a lot because it was kind of a hard problem. And he asked a lot of good questions. Now, what's my story? What's my story? Well, I first read about Milner's invariants when I was a beginning graduate student, maybe about a year. I actually entered graduate school knowing quite a bit of mathematics, quite a bit of topology. And already, Milner had become a sort of hero for me. You know, a guy who, I mean, he writes so beautifully. His work is just so understandable. And of course, every subject he taught, he did seminal work. He did groundbreaking work in everything he did. And some of his lesser known results are better than most of us will ever do in our life. Just a truly great mathematician. Possibly, one could argue that Milner was the greatest mathematician born in the 20th century. Some people would disagree with that strongly, and that's fine, right? But you could make that argument. You could at least make the argument. And I thought to myself, wow, well, you know, what did a guy like that do in his PhD thesis? So I went down to the library and I looked up his thesis. And it was this work, and I looked at that and I thought, wow. You know, I read it some and tried to understand it. And I'm telling you the truth. I mean, I thought to myself, you know, that's really amazing. I mean, I could tell. I'd heard about it, this stuff. I knew that this stuff had been very influential. People were still working on it. There were interesting questions. I could see that it had a certain level of depth and interest to it. I mean, I could look at this and see that this was a remarkable piece of work. But I swear to you, I thought to myself at the time, if this is what somebody has to do in their thesis, to go on to become possibly the greatest mathematician born in the 20th century, well, there's hope for all of us. Well, 2 or 3 years later, I'm nearing the end of my thesis, and lo and behold, just by chance, my work was drawn towards Milner's invariants. And so I went down to the library to get that paper again, because I knew I had to understand it more deeply. And that was when I discovered it was his undergraduate thesis. Oh, well. Okay, so these are Milner's invariants. Now, Milner asked a lot of interesting questions, most of which have been answered. Although there are still lots of interesting questions to ask, the ones that Milner asked initially have been, well, most of them have been answered by now. But it took a long time. It was well into the 1980s, late 1980s, before people began to answer these questions. 30 to 35 years later. But let me just make a couple of comments first, and then I'll tell you what some of his open questions are. So here's a little exercise for you to think about, all right? That mu bar of ij is the linking number of ki in kj. I take the ith and jth component of my link and I compute the linking number. And that's the Milner invariant of length 2. Those are the Milner invariants of length 2. So classical invariants that were much easier came out of this, right? One way to define the linking number is I take the complement of one of the knots, and that's a that has homology z, first homology z, and I take the homology class of the other in there. That's the linking number. Okay? So that's something you can think about. It's not too hard to prove. You could probably see that. Now, there's another thing I can note. So this says, so let's make a little comment, make another note, that f mod gamma k of f is isomorphic to pi mod gamma k of pi for all k implies that the pro-nilpotent completion, so I'll tell you what that is briefly. Pro-nilpotent completion of completion f hat is isomorphic to pi hat. So what is the pro-nilpotent completion? Well, I have this tower of groups, pi mod, I have this tower of groups. I have pi mod pi, my gamma 2 of pi, I have pi mod gamma 3 of pi, I have pi mod gamma 4 of pi, and I can keep on going down like this, right? And so I can take a look at elements, say G2, G3, G4, all the way up through the entire tower that you have the property that Gi plus 1 goes to Gi. Right? And that's a subgroup, right? That's a subgroup. That's called that's pi hat. That's called the inverse limit of pi mod gamma pi, inverse of pi, and it's a subgroup of for all k of pi mod gamma k of pi, and that's called the pro-nilpotent completion. And we'll think of that as having the trivial topology. That is points I mean, it's a discrete group. It's a discrete group, not the product topology. It's a discrete group. So we could talk about that. And so if these towers are isomorphic, then these groups are isomorphic. Right? It's a little observation. Now, Stallings proved in the 60s Stallings proved that Milner's invariants are concordance invariants. They're not just link invariants, isotopy invariants, but they vanish on slice links. Right? So Stallings, 1960s, Milner's invariants are concordance invariants. And there really aren't a lot more theorems that anyone proved until the 80s. Though a lot of people worked on it. Massey worked on it, Levine worked on it. Lots of very big mathematicians, famous mathematicians worked on this problem. And people couldn't make much progress. Vladimir Tureyev and independently Richard Porter showed that Milner's invariants vanish if and only if certain Massey products in the cohomology ring vanish. So that was a nice result and a very important result. And pretty much that's what people knew until the 1980s. So what questions did Milner ask? Right? What questions did Milner ask? So, right, the Milner invariants vanish if and only if this is true. Right? So, Milner's questions. Well, let's state a few of them. I'll state, say, 3 questions Milner asked about. What does it mean geometrically for mu bar L of length less than or equal to k equals 0, or for all of them to vanish? What does it mean geometrically to say that Milner invariants vanish? Right? That's a good question. Which invariants are realizable? And what relations hold among the mu bar invariants? Now, I'm going to take a moment and restate this problem. And then I'll state one third problem. Both of these questions are really well known now, or understood in some sense, in some very good sense. We'll talk a little bit about what the solution of those are. And the third question is the one that's most meaningful. And the answers to these questions are relevant to the third question. But first of all, let's think of this differently. Let's let CK equal links with vanishing Milner invariants. Vanishing mu bar of length less than or equal to k is 0. And then we'll define L naught is equivalent to L1 if mu bar L of length k plus 1 equals mu bar L of length L0 equals mu bar L1 of length k plus 1. Right? And it turns out it's not too hard to show that this is an abelian group. Right? And it's just the most obvious notion of connected sum you would want. You take a path from the first component of one to the first component of the other and just do a connected sum along those. And do the same for all the components. Now, there are lots of ways to do that. But this group, it doesn't depend on which way you choose. Right? And so the question, which Milner invariants are realizable and what are the relations can be summed up in the statement, what is C? What is CK? I guess we should call that CK. We'll call it CK. Right? What is CK? Maybe I want to shift this by 1 here. Let's do k minus 1 is 0, and then this is length k. And that's what we'll call CK. So what is that group? It's a good question. The third question that Milner asked was, how can we define, say, transfinite versions of these invariants? That is, how can we extend them further? There are lots of examples. He gave some examples of links which have all vanishing Milner invariants, but they're not the trivial link. So what can you say about that? How can you define, for example, these are indexed by the integers. Well, the first infinite orbital is omega. So how would you define, How would you define mu bar of length omega? Or omega plus 1, or omega plus 2? How would you go about doing that? That's a hard and interesting open question. That's the one that hasn't yet been fully answered, although we have recent progress on that. That I'll talk about at the end of the talk. So what I'd like to do now is to give you a completely different approach to Milner's invariants. Right? This approach was developed by me some years ago. And it does allow me to answer, it does allow one to answer the first two of these questions well and make small progress or maybe big progress towards the third one, at least come up with a candidate. So what's the different approach? Well, let's see. So assume L in S3 has mu bar L of length less than or equal to k equals 0. Right? Now that's the same as pi. Well, that implies that that there's a map, right? There I have the map from F to pi, which is given by the meridian curves. And if I mod out by gamma k, these are isomorphic. Now, recall that maps from x to y, this is pointed homotopy classes, lie in one-to-one correspondence to homomorphisms from pi 1 of x I'm sorry, I don't mean that. Maps from x to, I'm sorry, that's not what I meant. Right? Let's see, what do I want to say? That's what I thought, right. So if I have a group G, I can create this space called a KG1 space, an Eilenberg-MacLane space. And this is a space whose fundamental, it's a CW complex, the fundamental group is G, and all the higher homotopic groups vanish. And homotopic classes of maps from X into KG1 lie in one-to-one correspondence to maps from from homomorphisms from pi 1 of X into G. Right? That's a standard fact about Eilenberg-MacLane spaces, sort of the fundamental property that they satisfy. And so, the map from pi to F mod FQ, I have this map from pi. If the Milner invariants of length less than or equal to k vanish, I have this map from pi to gamma k to F mod gamma k of F. And that corresponds to a map from the exterior of the link to the k pi 1, kf gamma k of F1. And now I can take a look at the boundary of this. Well, that's L cross S1. And in here, I can just take the wedge of circles. I'll just make an inclusion of the wedge of circles into this space. Turns out you can always, up to homotopy, you can always make a map and inclusion. You take the mapping cone. So I take the map from the free group into here. That gives me a map from, this is a space whose fundamental group is free, into this space. And I just make it an inclusion using the mapping cylinder. Okay? And up to homotopy, I know what this map does. The longitudes are trivial in this group. So the longitudes homotopically map to points here, whereas the meridians go to the generators here. So up to homotopy, after a little homotopy near the boundary, I can assume that this is just projection onto the wedge of S1s. Right? It takes a ki cross S1 to the ith S1 here by projection. Okay, so what do I have? I can get the sphere back by taking EL and take its union over the boundary with L cross D2. Right? And since L cross S1 maps to a circle, L cross D2 will map to a disk. So this gives me an extension from S3 to K F mod gamma K of F1 union over this wedge of circles with a wedge of disks. And let's give that space a name. For convenience, we'll call that K sub k. Now that actually has another thing it depends on. It depends on the number of components of the link, because that determines the rank of the free group. So I have to add some, in theory I should add another thing to indicate how many components I have. This space depends on the number of components, because the free group changes depending on how many components I have for the link. But I have this map here, and so that gives me an element. We'll call this phi, and phi is an element in pi 3, the homotopy class of phi is an element in pi 3 of kk. Okay? So I defined these invariants many years ago. And let me tell you the results, some results about them. So this is a theorem. Everything in this theorem will be due to me except for I think one point I mentioned some joint with a collaborator, Kiyoshi Agusa. So I have L in S3 with a mu bar invariance of L of length less than or equal to k equal to 0. Okay? So that means that theta k, so then there exists a concordance invariant. Theta k of L in pi 3 of kk satisfying, well, the following. I'll give a bunch of different statements. Some particular advantages on slice links. Well, let's see. For any x in pi 3 of kk, there exists some L in S3 with theta k of L equal to x in pi 3 of kk. I'll talk later briefly about how that statement, roughly how that statement is proven. It's really remarkably easy. But every one of these invariants is realizable. They're structured to be that way. Right? There exists a map, kk plus 1 to kk. Of course there's such a map, right? If I take the map from f mod fk plus 1, f mod gamma k plus 1 of f to f mod gamma k of f, it gives me a map of Eilenberg-MacLane spaces. It takes generators to generators, so it gives me a map from this space, above the k plus first to the k space. And if the mu bar invariance of L, well, let's say it even differently, and the mu bar invariance of L of length k plus 1 vanish, if and only if theta k of L is in the image of pi 3 of kk plus 1 into pi 3 of kk. So that says I have this element, right? I have this map from S3 into here. If it lifts at all, even up to homotopy, if it lifts, then in fact the Milner invariants of length k plus 1 vanish. On the other hand, that takes a proof. On the other hand, if the Milner invariants of length k plus 1 vanish, this invariant exists and clearly heads down to this one. So that's an if and only if, right? If and only if. The group CK is isomorphic to the co-kernel. CK plus 1 is isomorphic to the co-kernel of pi 3 of kk plus 1 into pi 3 of kk. And that's known. You can compute, well, it's not known, but you can compute that. That's z to the number of components, I'll call it times L, I guess I want k plus 1. I wish I had done it differently. Minus z to the lk, where lk plus 2 rather, where lk is the rank of gamma k of f mod gamma k plus 1 of f. That's a free abelian group, and you compute its rank. And there's a formula for that. That's an old formula for that goes back to Magnus' work. So in fact, that answers the question about the number of independent Milner invariants and what can be realized completely. You can say what it means for it to vanish, too. Theta k of L equals 0 if and only if there exists a disjoint collection of surfaces, Fi in D4, such that the boundary of the surfaces, the boundary of this collection of surfaces equals the link, and if G equals pi 1 of the exterior of those surfaces. Then G mod gamma k plus 1 of G is isomorphic to F mod gamma k plus 1 of F. Right? So in particular, that's always true if it's slice. If it's slice, those disks, it bounds disks, it's not hard to compute and see using a theorem of Stallings that this will be true for every k. What this says is, if this invariant vanishes, the link bounds surfaces that look like a slice, a slice for the link to the k plus first lower central series. Right? And finally, to answer the question about what it means for these invariants to vanish, it's a result of a Gusa and I, who proved that theta k of L, this was really quite hard to prove, to be honest with you. Theta k of L vanishes if and only if the mu bar invariants of length less than or equal to 2k are 0. So in fact, the Milner invariants of an even length vanish tell you that to the k plus first lower central subgroup, it bounds surfaces that look to the k plus first lower central subgroup like slice disks. So this really is approximating slicing the knot in the sense that it approximates it as far as the lower central series can see. Okay? Now what about question 3? That's the next place to go. What about question 3? Can we say anything at all? Well, we can say a little, because we made an observation that will help us. We talked about the pro-nilpotent completion. Right? So note, all mu bar invariants of L are 0 if and only if the map from meridians to the group, the exterior, the group of the link, gives you an isomorphism modulo when you take the pro-nilpotent completion. So now I can take the exterior of the link, and I can map it to, well, its nilpotent completion, and via this isomorphism to kf hat 1. And once again, I have the boundary, L cross S1, and here I have the image of the free group, and I can take this map, and you can see that up to, so the longitudes lie in the intersection of the lower central series. They map trivial to here. They map trivially into here. And so it follows that this is up to homotopy, just projection. So after a little homotopy on the boundary, you can make it projection to the wedge of S1s. And that implies you can define an element we'll call theta omega of L in pi 3 of k f hat 1 union over a wedge of circles with a wedge of 2 disks. And we'll call that space k omega. And that's a candidate. That's a candidate, a good candidate for a transfinite Milner invariant. Right? What would you mean by transfinite Milner invariant? Well, there's a good candidate. Well, unfortunately, I defined that many, many years ago, and a lot of people tried to compute this group, and it was really hard to compute. Really hard to compute. We couldn't even tell if this group was 0 or not. So maybe I'm just defining the 0 invariant. Right? I mean, you know, it turns out that this group maps onto the third homology of the pro-nilpotent completion. But nobody knew the third homology of the pro-nilpotent completion. We still don't know the third homology of the pro-nilpotent completion. Nonetheless, I do have a new theorem, or rather, we have a new theorem. Mikhailov and myself. Roman and I can prove, right? Roman and I can prove pi 3 of k omega is uncountable. So it became a better candidate for a transfinite Milner invariant. It's not just non-zero. It's huge. It's absolutely huge, right? It's absolutely huge. Now, you might hope that however I proved that you could realize the previous invariance would work here. But it doesn't. In fact, there's no hope for it working, because a little combinatorial argument about triangulating 3-space and using, you know, and taking cellular maps will tell you that there's at most countably many links. So how could I ever realize an uncountable collection of invariants? Right? So something goes wrong. Something goes wrong. It's evidence, but it's not where we want to be. Right? It's not where we want to be. So what I would like to do in the remaining minutes here, let's see, we started about 7 minutes late. I got about 7 minutes maybe? Okay. What I'd like to do with I don't want to run over, but what I'd like to do with the remaining moments is first take a few minutes and talk about why it is that realizability fails. Right? And the questions that motivates. And then I'm going to take a couple of minutes more and list some things I'll talk about next time in a continuation of this discussion. Okay? So that's how I'd like to finish. So first of all, how do I realize? It's really very simple. It's an elementary argument, x in pi 3 of kk. Right? Well, there's an obvious thing that just jumps at you when you look at it. I have a map from S3, we'll call it phi x, into k sub k. Now let me remind you what this is. This is f mod gamma k of f1. It's the Eilenberg-MacLane space. It's the classifying space of that discrete group. Union over a wedge of circles with a wedge of disks. Well, all I need for transversality is that I have these disks here. Right? They're nice smooth manifolds in there, the disks, right? The open disks. So I can make this map transverse to the center point of the disks. So let's call the points in there, we'll call P the center points. Okay? And I'll make the map transverse to P, and then I take phi x inverse of those points. And that gives me, well, that gives me something of the form, I'll call it K1 through Km contained in S3. Unfortunately, those Ki's might have lots of components. Ki's may be disconnected. So what do I do to fix that problem? Well, it's a little observation in the commutator calculus, or, right, to check and see that something wonderful happens. If I take pi 1 of the exterior of these knots ki, I have a map from that into f mod gamma k of f. Right? I just remove the disks, and I remove a neighborhood of those knots, and I get a map from the exterior into this space. So a map of pi 1 is onto. Okay, so it's an exercise to check that. So what does that help? Well, it helps in the following way. Suppose I have two components. Right? Suppose I have two components. These are both parts of ki. And suppose, well, okay, so but I need to make them one component. Well, I take something that maps to the base point, a point in this knot that maps to the base point, and another one, and I just draw an embedded arc between them. Unfortunately, the image of that embedded arc is a loop in here, but it may be non-trivial. But that's okay. If it's non-trivial, I just add a loop here, so now the composition is trivial. And then I just change that to make it embedded. And then it's not hard to show that you can connect these knots up along that arc, and you don't change the homotopy class of the resulting map. Okay? And that allows you to make it to realize the invariant. So it's just a little surgery theoretic argument, 1 and 2 handles, done using by first noting that this map is onto. Well, what happens if I use the pro-nilpotent completion? Well, I start off with S3 and I go to KF hat 1. Right? Union a wedge of circles over a wedge of disks. But now when I take E, the exterior of these KI's, and I map to F, I take pi 1 of that, and I map to F hat, it's not close to being onto. It's not even close to being onto. Right? In fact, how could it be? This is a countable group. This is an uncountable group. So that's a serious problem. So if it's not onto, I can't do this trick, which allows me to connect them up without changing the homotopy class. Well, one observation you can make is that I can change. I'll talk more about the underlying concept I'm going to mention in a second. I could change this link by a concordance without changing this invariant. Now, the concordance is a funny notion of concordance because components have the knots have many components, right? But I could still do that. And as I do that, the image of the fundamental group might change. Now, you might, for those who did attend my colloquium talk, I talked about how when knots are concordant or links are concordant, their complements are homology cobordant. That is, they are cobordant as manifolds, rel boundary, by cobordisms that have the homology of a product. And so immediately you get the following question that comes up. How does pi1 of a manifold, of a 3-manifold, change, some 3-manifold change under homology cobordism? And that question underlies trying to get an answer to realization. Okay? And we're going to answer that question, at least in some sense, next time. And we're going to see how close we can come to realizing this invariant. Now, let me be clear. The problem of finding transfinite Milner invariants is still open. It's not known if this invariant can be realized. But we can say more than it's said here. We have more we can say that makes us closer to the answer than it may appear. Certainly, seeing that this group that the invariant lives in is uncountable is a huge step in the right direction. For the first time, we have hopes that there's something real there that we can have. It's not just the zero group that the invariants live in. So what am I going to talk about next time? Okay. Okay, so next time, there'll be a lot of very new things and elementary things next time. I'm going to build on this, but only later on in the talk. Okay? We'll start off with more basic things again, to build new tools. So I'm going to ask, question, let's call this question star. Okay? So the first thing I'm going to talk next time is I'm going to talk a little bit about, now maybe not the first thing, but I'm going to talk a little bit about this question. It's going to be an underlying theme for the next talk. Okay? And towards that question, I'm going to talk about something due to Jerry Levine, called Levine's algebraic closure of groups. For people who know a lot of homotopy theory, the notion of algebraic closure of groups is very close to the notion of homology localization of spaces. It's very similar to homology localization of spaces. Now, after I've done that, I'm going to spend a lot of time with that. I'm going to define it. I'm going to give examples. It's a beautiful construction. It's easy to understand. It's really a really lovely thing to look at and to understand a little bit about. I'm then going to return a little bit about and I'm going to return to study and refine theta omega of L in pi 3 of k omega. And the work that I'm going to do that does that is all due to Levine. Right? This is Levine. In fact, it was why he defined this notion of algebraic closure of groups. And then I'm going to start talking about the more general question. I'd like at least some, if we can't completely resolve the question of whether or not transfinite Milner invariants exist, what I'll do is I'll define an analog of transfinite Milner invariants for homology cobordism of 3 manifolds. And I'll show you that that exists and can be realized. Okay? That there are infinitely many things that can be realized that way. So we will define an analog of Milner's invariants, of Milner's transfinite invariant in particular. A homological invariant, not a homotopy theoretic one, but a homological one, for homology, to study homology cobordism of 3 manifolds. And give evidence. Who knows what evidence means? I think it's evidence. Maybe others won't be convinced. Evidence using that Roman and I have really made significant progress towards finding transfinite Milner invariants, right? The transfinite Milner invariants exist. Okay? Okay, I think that's everything I wanted to say today. I don't think I'm too much over. Thank you.